Alright, so this video is going to focus on part 6 of the notes, I believe, Dalton's law of partial pressures. I've given you a couple of equations at the top, and the biggest thing you need to know is that the total pressure is always going to equal the sum of the individual pressures that are making up your mixture. And if you're collecting a gas over water, you would only have two gases in your mixture, the gas you're collecting and then the water that is also exerting a pressure on the gas. So that's the first set of equations. Your units need to be consistent. The second one I don't want you to get too stressed about. I'm giving that to you just to show you the proportions between partial pressures and volume. But I'm going to do an example. Hopefully that'll make it a little bit simpler for you. So our first example involves a mixture of atmospheric components, nitrogen and oxygen, and we're given their partial pressures. Partial is just the part they contribute to the overall pressure when they're combined together as a mixture. And then we're asked to find the partial pressure of carbon dioxide, also known as CO2, if the total pressure is 105.21 kPa. So we have three components making up our mixture, and so those three individually, when added together, will give us the total pressure. This law is a little bit different than the other laws we've done. It only involves one variable, pressure, and we don't use multiplication and division nearly as much. We tend to just add and subtract. So now that we have our equation, we can substitute in the quantities we know. We know the total pressure is 105.21 kPa, that nitrogen's pressure is 80, oxygen's pressure is 21.30 kPa, and we want to find the partial pressure of CO2. To find the pressure of CO2, we're going to apply our algebra rules. We all have our pressures in kPa, so that's consistent, and they all have two decimal places. And when we add and subtract, we want to round our answers to the fewest decimal places, so our final answer should have 2 in terms of decimal places. Before we get there, we need to combine our constants on the right side of our equal sign. So we're going to add 80 and 21.3 together. And when we do that, we get that 105.21 is equal to 101.30 kPa plus the partial pressure of CO2. To get the partial pressure of CO2 by itself, now we're going to need to isolate the CO2 by subtracting the 101.3 from both sides of our equation. And when you do that, you'll get the partial pressure is 3.91 kPa. If you substitute that into the partial pressure of CO2, you would see those two added together give you 105.21 kPa. Our second example is hydrogen gas being collected over water. The temperature is listed because water's pressure that it exerts on other substances is going to differ depending on how warm the water is. And so you will see different vapor pressures of water given the temperature it's at. Whenever we're collecting something over water, we'll only have the two components making up our mixture, the gas we're collecting and the water that's doing the collection. Another way you can see total pressure, as you see up here in this example, is atmospheric. Atmospheric and total mean the same thing, and so we'll use that to set everything equal to. We're asked to find the pressure of the hydrogen gas. So our total pressure will be the pressure of the two gases, hydrogen, and the pressure of water. We know what our total pressure is, the atmospheric pressure, 103.6 kPa. We're trying to find the pressure of hydrogen, and we're going to add that to the pressure of water, 2.3 kPa. And the difference between the water's pressure and the total pressure will give us the pressure of our hydrogen gas. We don't have to add on the right side this time since we only have one constant. We have one decimal place in both of our measurements, so we want to have 1 in our answer. So when we subtract the 2.3 from both sides of the equation, we get that the pressure of the hydrogen is 101.3 kPa. Some students have asked, how can this be harder? It would be difficult or more difficult if you had a different unit for pressure for your total pressure or for your water pressure, and you had to do some conversions to get them to be consistent. Pretty much the only other thing I could do is ask you to find the total, and that one's actually a little simpler because then you would just add. All right. The last two examples are going to be dealing with that proportions relationship I talked about. We've got a mixture that is 30% hydrogen and 70% oxygen by volume. And so what that's telling us is that if we were going to treat it like a pie circle, 30% of that circle would be hydrogen and 70% would be oxygen. And that together, with those relative percentages in mind, the total pressure would be 125 kPa. So what this is telling us is 30% of that total pressure is coming from hydrogen and 70% is coming from oxygen. So if I wanted to find the partial pressure of just the hydrogen, I would take 30% of that 125 kPa. However, I can't have a pressure of an individual gas that's greater than my total. So you see here that it's not 30, but it's written as a decimal form, 0.3. And that's the biggest difference. Basically, that fraction I showed you at the front, which is 30 over 100, which would give you the 0.3 as your fraction of hydrogen in your mixture. So 0.3 of 125 kPa would have 3 sig figs, and that should give you 37.5 kPa. You could do the exact same thing with oxygen, but instead of using 70%, you would change that to a decimal as well, and it would be 0.7. And 0.7 of the 125 kPa would give you 87.5 kPa. There's another way you could get oxygen, and that is knowing that hydrogen and oxygen make up your total pressure. You could subtract 37.5 from 125, and you would get that 87.5 kPa. Or you can just add these two together, and you will see that they too do add up to the 125 kPa total pressure making up this mixture. Now in this example, I asked you for both of the partial pressures of your mixture. I don't have to. I could ask you for just one of them. And something else I haven't brought up yet, please keep in mind your mixtures don't have to be just 3 things. They could be 2 substances, they could be 5, they could be 8, they could be however many you need them to be. This example also has 3 substances, 25% carbon monoxide, 65% carbon dioxide, and 10% oxygen. We're told what the total pressure is of our mixture, and we're asked to find the partial pressure of oxygen. So if we just want to find oxygen, we're going to take that 10%, convert it to a decimal, 0.1, and multiply it by our total pressure, 950 millimeters of mercury. We have 2 sig figs and 950 millimeters of mercury. Sorry, cat. And when you multiply 0.1 by 950, you will get 95 millimeters of mercury. The first 3 examples on your homework deal with the first example here on the video. The next 3, 4 through 6, deal with the second example. And these last 2 examples will help you with 7 and 8. If you have any questions, please feel free to let me know in class, study hall, before school, or after school.